All right, here's the plan for today. In both parts of lecture 10, we're going to have review for the exam next time. As we go, I'll talk about what to expect. And then the last 4 pages or so of the PowerPoint, I also have more specific details. So lecture A is about getting more depth about probability and means and standard deviations of random variables. Lecture B, we will introduce the law of large numbers and the central limit theorem. This basically takes us through at the end of chapter 4, and you are responsible for all these things on the exam next time. Yes, next class period, that for you guys is next Tuesday. It's something else for people in the future. Maybe people in the future that have even already had their first exam. Time frame for us, 10:45 to 12:25, so we'll start early. Don't forget that if you want to get more time. I have reserved this room, so nobody should take it from us early here. A note card is allowed, but I emphasize once again, that's just your security blanket. You want to study well enough that you don't need that note card, that you could do it without one. It's just there for your security. Because if you rely on it too much, it will slow you down. It'll make you more anxious when you can't find things you think you were trying to find and you can't find them. You want to understand stuff. You want to practice problems especially. Calculator will be needed. Make sure you can do all the things that we've done. Means, standard deviations, especially correlation coefficients and regression coefficients on a calculator. As far as the 5-number summary goes, you should be able to do that by hand after ordering the numbers. In fact, the calculator might give you the wrong answer as far as the quartiles go, based on how I described to find the quartiles. So you may want to review that old video about the quartiles and how to do that according to our books and my approach. I did just this morning put up some resources for studying on Moodle. So if we look at the Moodle page for you guys, maybe not a Moodle page for a future class. Down here there's 2 new sections. One says old exams and one says other exam review resources. So if you open up the old exams, I've got 2 old exams in there. One I called Exam 1 from fall 2012. Another one I called Exam 2 from fall 2013. When I've taught this before during a regular semester, I typically had 3 midterms rather than 2. I compensate with you guys by having a lot more quizzes. So my old Exam 1 went through section 4.2 in our textbook here. Your exam is going to go through all of chapter 4 through section 4.4. So the problems that you see here and the corresponding answers to some of them don't cover everything that's on the test, and there could be other things that are not on this old exam that could be on the test as well. But it's good to practice. You want to practice old problems, certainly, and I do have the answers to some of the problems here. But you're going to want to look at Exam 2 as well, which in a 3-exam semester covers sections 4.3 through 6.3. You're only going to want to look for chapter 4 problems from this old exam, related to probability and random variables and means and standard deviations of random variables. I've got answers to some of them as well. But the other problems that are from chapters 5 and 6 you can ignore. Some of them are still probability problems from chapter 5. Again, we focus on mostly on the idea of probability, basic probability distributions, and means and standard deviations of random variables. That's our focus in chapter 4. I have more resources in this other exam review resources, including not specifically exams, but just more questions to practice. Stats review problems from sections 1.1 through 4.2, which is exam 1 for semesters that have 3 midterms. We again have 2. And solutions to those that are a lot more detailed than my answers to the old exams. I show you how to do the problems in detail. And I have another one that's problems from sections 4.3 through 6.3. Again, just focus on the chapter 4 ones for us, and solutions for those. I do include stuff that's not in the book, SS formulas and SSE calculations included. That's something you should know how to do for our test, okay? well as possibly today's quiz and future quizzes. So you're going to want to look at both of these links on, both of these tabs on Moodle. Okay, you're going to want to look at the old exams and the old extra resources here that have more types of exam problems. You're going to want to practice them all. And you're probably going to want to time yourself, like with the old exams. Maybe give yourself less than I'm giving you. Okay, I'm giving you, what is it, an hour and 40 minutes, I think? Okay, maybe give yourself just an hour and a half. You'll feel the time pressure. Try to do it without a note card. That'll give you good feedback about where you're at as far as your understanding goes. Okay? Then you check your answers, compare with the neighbor. Try it again then. See if you do better. You're going to want to put a lot of time in. You're not going to want to wait for next Monday night, okay? You're going to want to practice some along the way, maybe a little bit each day. That's probably the best way to do it if you think about the make it stick thing. Don't forget about the math lab. They can help. I know the number of stats tutors is a little disappointing for some people. However, tonight, there is a stats tutor, Amy Sukup, who will be there. I'm not sure if she's there the entire time frame, but she's somebody who should be able to help you. In fact, she's one of your graders. And Sunday night, another student, Lydia Johnson, can help. She's not one of your graders. Again, I'm not sure if she's there the whole time, but she's somebody who can help. The other TAs might be able to help too, but they are definitely specific statistical analysis TAs. Okay? So I'd get going on it tonight. I would study some tonight. By the way, you won't have any homework due next Tuesday. You're going to just be prepping for the exam. Okay? Nothing to handle next Tuesday. All right, so I'm going to go through and talk about what we've been talking about recently, as well as some new stuff that is still going to be on the exam. The new stuff being the law of large numbers and central limit theorem. Two big things, and we're going to just get a brief introduction to them, so you're going to, on the exam, need to know the basics about them. You're not going to need to know them in a ton of depth. But I do want you to understand the basic ideas about them. So I'm going to go through a lot of the slides I've gone through already, fairly quickly. Do your best as usual to pay attention. Keep your minds on. Really think when I talk. Oftentimes, every single word I say is important. Okay? So then you may want to watch parts of the video again to try to recatch some of the things that I say. And I hope those timestamps that I put on the videos are helpful. I try to make them as helpful as I can be to help you find things quickly. You should be able to deal with conceptual questions related to graphs like this. What are these graphs? These graphs were illustrating the idea of sampling distributions and really probability in a sense, and the idea of populations and samples, parameters and statistics. I was using equals ran between 1 through 10. First of all, to create a graph like this, you should understand what this graph is about. I'm using ran between 1, 10 over and over and over again, so I get a bunch of different random numbers between 1 and 10. I'm imagining that sampling from a population with a population proportion P of 0.6. That was the people who ate out last week, right? That was our example. 60% of the population ate out last week. That's what we're imagining. So the idea was that digits 1 through 6 represented people who ate out last week, and 7 through 10 represent people who did not eat out last week. I kept track of the sample proportion. These values that you see graphed here are really p hat values, sample proportions, that are supposed to estimate p. But I keep going, I make my sample effectively bigger and bigger by continued sampling, continued trials. And the idea here is that p hat gets closer and closer, generally speaking, with ups and downs, to p, to 0.6. 0.6 would be right about there, and you can see it is generally getting closer. There's lots of ups and downs, big ups and downs at first, because when your sample size is small, one new trial can greatly affect the value of p hat, but then the jumps get smaller and smaller and they approach the population proportion. That actually is analogous to the law of large numbers that we're going to talk about today. It's a similar kind of graph that we're going to talk about with sample means later today. What's this graph? This is a histogram that's an approximation to the shape of the sampling distribution of the sample proportion with the population proportion p equals 0.6. The true sampling distribution would be shaped fairly much like a normal curve. It's actually not exactly a normal curve because technically p hat is discrete, not continuous, but it's well approximated by a normal curve. It should be centered on the true population proportion, that's a 0.6 right there, if I'm doing random sampling, and I'm assuming rand between does that. That's meaning it's unbiased. Okay, about half the values of p hat will be above 0.6 and about half are below. Is it exactly half above and half below? Not exactly necessarily. Approximate. Okay? And there's a certain amount of spread that you measure by the standard deviation of the sampling distribution, which would be this distance between the vertical line through the peak and the inflection points on either side. This is not drawn perfectly. Okay? So it's an approximation to the sampling distribution because it's not really a probability distribution. We're counting a frequency here instead of a relative frequency. But it gives you the idea of the shape. It's basically symmetrical. Okay? So you should understand what those graphs are telling you. I can ask you conceptual questions on the test related to graphs like this. Can you describe the meaning of these graphs? And I just described them for you. Maybe you'd have to write out your own description. Maybe I would give you to you a multiple choice question. Okay? Probability. And by the way, some of these things could be on the quiz today too. Probability is a number we assign to an event in a random environment. That's a measure of how certain we are that the event will occur. You can be wrong in your assessment of the probability. You hope you're fairly close in your assessment of the chance that something will happen. It's a number between 0 and 1, or as a percentage between 0% and 100%. Again, measuring how certain you are. When you flip a coin vigorously, for example, it makes the most sense to assign a probability of heads as 0.5 or 50%, though that's not exactly right, but it doesn't really typically matter as long as it's close to right. I'll skip over this slide. We talked about that last time. I did do a simulation of coin flipping on a spreadsheet with rand between as well, and created a toss. Well, okay, this is from the book, the toss series graph. It's analogous to the previous one, except the population proportion is 0.5 instead of 0.6. The population proportion and the probability are really the same. It's like when you flip a coin, I'm imagining I'm flipping a coin from the population of all flips that all people have done for all time, and all people will do for all time in the future. Okay? That's like the population. It's basically infinite, maybe, if you imagine forever into the future. Flip coins in heaven here, okay? The idea is that P, that population proportion of 0.5 is the same as the probability. And by doing the actual sampling trials here, we are in effect estimating P, and they're really like P hat values. Again, they're like sample proportions. But again, the idea is they approach the true probability, and the number of trials, the number of classes keeps getting bigger and bigger. And again, that's sort of like the law of large numbers that I'll talk about for means later. Probability models consist of sample spaces. Okay, we consider some basic examples of sample spaces with coin flipping, where I write down some H's and T's. And I could also count the number of heads, and I could think of sample spaces related to that random variable. Like if I flip a coin 4 times, I could get 0 heads, or 1 head, or 2 heads, or 3 heads, or 4 heads. And I could consider that to be my sample space and assign probabilities to those. Just done simple examples there, okay? Basically find out the probabilities by listing out the possibilities and assuming each of those runs of H's and T's is equally likely. We'll do more complicated kinds of sample spaces in Chapter 5. Okay? We'll keep it simple if this is on the quiz or the test. Probability models in those kinds of situations are made with charts. It's like a discrete random variable. Again, the number of heads could be 0, 1, 2, 3, or 4, finitely many. And I can assign probabilities that can't be negative and I have to add up to 1. All these properties are important to know. That's the way probability models work. You should understand probability notation as well. When I write P of E, that entire expression represents the number, that is the probability of E occurring. Okay? And you say P of E. P is not a number, E is not a number. E is just a letter that represents some event. Okay? It's like a shorthand. just a symbol. P is sort of like a function. It's like an f of x notation, where f is the name of a function. It's just telling you you're going to sort of plug the event into P and get a number. P of E is the number. That whole symbol represents the probability of E occurring. Okay? You should know that. Talked about finite sample spaces already. What about infinite sample spaces? We can use density curves. Actually, it's more than infinite sample spaces. It's really a continuum of values, like a measurement of a height or a weight or an amount of time. Those are all numbers that can be measured on a continuum because you can have an arbitrary amount of accuracy, essentially. So it's best to use density curves to find probabilities there. How do you find what the right density curve is in real life? You have to look at past data. You have to look at past data. Not always. Sometimes you can do it theoretically, but oftentimes you have to look at past data. Graph a stem plot or a histogram. Look at the shape. Oftentimes it'll look like a normal curve, but it could be uniform like this, or it could be triangular. But the key idea is once you've got a good density curve that models the data or models the random situation, you find probabilities by finding areas. Okay? You should know that for the quiz and the exam as an idea. I'll tell you on the exam, you should be able to also do calculations of areas. On the quiz, you won't have to actually calculate areas, but you should know the idea. I will again provide you a table if you need to use table A with the z-scores, the standard normal curve. I will give you the table of random digits as well. If I give you a uniform or a triangular, you should be able to find the area by using geometry. Areas of rectangles, areas of triangles, areas of trapezoids, if you want to look that up. You should be able to do that, okay? And you should be able to use the probability notation like I showed you last time when I was talking about the hummingbirds. And we used the fact that the weight of the hummingbirds was normal, and we converted to a z-score within this notation. If you don't remember what I did, you're going to want to go back and watch the last class's video. I think it's near the end. It's in lecture B. Again, this slide just emphasizes the area. When you have a continuous random variable, essentially there's no chance that x will equal something exactly. You know, what's the chance that somebody's that I pick is going to be exactly 6 feet tall? Exactly, down to the nearest micron, even more precise, okay? Not like pretty much the chance is 0. We do say plenty of people are 6 feet tall, but that's with rounding to the nearest inch. Okay? With a continuous model, the chance that the variable is going to be exactly something with infinite preciseness, if you will, is 0. We can only think about intervals of values and then calculate the area. Lines have no area. Okay? The area under the curve above some number is 0. So the probability that it equals some number is exactly 0. And again, likewise with these inequalities, it wouldn't matter whether you put less than or equal to or less than. You get the same answer. It's the same area with continuous variables. With discrete ones, it matters. You've got to focus on which values you're talking about. There are a bunch of rules here. I haven't had time to go over these at the moment. And I think I'm not going to test you explicitly about these here for Chapter 4 in this first test. They will definitely come up in Chapter 5. We'll talk about these a lot, and some other rules. It is in this slide. You can think about it if you like, but mostly we'll talk about that in Chapter 5. Random variables, they come in 2 types, discrete and continuous. You should know that. You should be able to identify discrete versus continuous. Certainly when a variable, random variable again, measures a numerical value, it's a quantitative thing. It can be discrete, it can be continuous. For us, mostly, discrete means a finite number of possible values, like the number of heads, a certain number of flips. Okay? Number of earthquakes in a certain amount of time. That technically is discrete as well. We're counting. There might be no theoretical upper limit, or you might not know an upper limit, so in a sense that could still be an infinite sample space. But in practice it would be finite. On the other hand, continuous ones, you're talking about values in a continuum. Again, like I mentioned, weight, time, height, length, distance, speed. Those are all continuous quantities that can be measured with an arbitrary degree of preciseness. So you should understand the difference and be able to identify those. Our main use of random variables will, in chapter 6 and beyond, will be to describe sampling distributions for sample statistics like p hat and x bar. And we're going to do that some today, also with the law of large numbers and the central limit theorem. Actually, we've already described it for p hat. We're going to describe it for the sample mean x bar today. But we want to understand random variables in more depth in other situations too. I've got a coin flipping description here. I think I'm not going to spend time with this again today. Maybe I'll come back to it after the test next week. But it can be simulated. This is focused on the number of heads in 4 flips. And this is a probability distribution for that. Although if I gave that to you, you should be able to verify it's a probability distribution. Those probabilities are all positive, non-negative I should say, and they all add up to 1. By the way, again, this notation here, k is representing the different values of the variables 0, 1, 2, 3, and 4. And you read this notation as the probability that x equals k. This symbolism inside here is like the e in that other notation. It's a shorthand, in this case, describing the probability that x equals k. K could be 0, 1, 2, 3, or 4. So this is the probability that x equals 0. This is the probability that x equals 1. This is the probability that x equals 2, etc. That's how the labeling goes. Just shorthand notation. And this is discrete, so we can assign a positive probability of x equaling certain values. I'll come back to the simulation for this again probably next week after the exam. I think that's important enough to do. And I've got some results from when I did trials with that. Let's move on. Okay, this is important for what I'm about to talk about is not on today's quiz, but it could be on the test. Okay? Although this is still related to that example. I think this is worth talking about. So this is related to the previous example that I said I'm going to skip over here for the moment. But I'm not going to skip over this slide. Okay? Because I want to give you a brief intuitive feel for why those formulas I talked about at the end of class the other day work, at least for means. Imagine flipping a coin 4 times. Okay? The probability distribution for that is what you see right here. With a fair coin, where each flip comes up heads or tails 50-50, you would expect to get 0 heads about 1/16 of the time. You flip a coin 4 times, there's 16 possibilities in the sample space. Each are equally likely, and in only one of them do you have 0 heads. You have T, 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 all tails. In 4 of them, 4 out of 16, you have 1 head. H, T, 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 H, T, T, etc. In 6 out of the 16, you have 2 heads. For example, H, H, T, T, etc. List out the possibilities, etc. This is the probability distribution. So if you flip a coin 160 times, well, excuse me, I said that wrong. If you flip a coin 4 times, record the number of heads in 4 flips, and then repeat that 160 times, meaning you really flip the coin 640 times, 160 runs of 4, you should expect that these probabilities reflect approximate fractions of the time you get these numbers of heads. You should get 0 heads 1/16 of the time, meaning about 10 out of 160. 1 head about 4 out of 16 of the time, 1/4 of the time, 40 out of 160. 6/16 of the time you'll get 2 heads, 60 out of 160. Again, realize what I'm imagining doing. Flipping a coin 4 times, counting the number of heads, and then doing that over and over again 160 times. Each time counting the number of heads and writing that number down. Because that's what you would expect approximately, you could also approximate the mean of such a data set, just theoretically. How? It's essentially what's called a weighted average You imagine you'd have 10 zeros, 10 out of 160, 1/16th of the time, you get a 0. 40 ones, 40 out of 160, 4/16ths of the time, you get a 1, approximately. This is a theoretical estimate. I'm not actually doing the simulation. 60 out of 160, 6/16ths of the time, you get a 2. 40 out of 160 times, you'll get a 3. 10 out of 160 times, you'll get a 4, approximately. Add up the sum of all those 0s, 1s, 2s, 3s, and 4s, meaning use these weights, how often they occur, to do the adding. You have 10 zeros, 41s, 62s, 43s, 10 4s, and divide by the number of trials, 160. You get this, you get 2, which is what you would expect for the mean, right? 0, 0, 1, 2, 3, 4, it's a symmetric distribution centered at 2. 2 is the most likely value. And it's also what you would expect from the average, because that distribution that I showed you in the table is symmetric. If you rewrite that formula like this, which can be done by properties of fraction manipulation, I could break this fraction up into the sum of 1, 2, 3, 4, 5 fractions. 10 times 0 over 160, 40 times 1 over 160, 60 times 2 over 160, 40 times 3 over 160, and 10 times 4 over 160. I could also reduce those fractions. 10 over 160 is 1/16, 40 over 116 is 4/16, etc. And I can bring the numbers 0, 1, 2, 3, and 4 out in front, get the same answer. And what this illustrates right there is that formula for the mean of a random variable. I'll write in the sloppy way on the board. The mean of x is the sum of x times p for a finite sample, for a finite random variable, discrete random variable with finitely many outcomes. Take the possible x values times the corresponding probabilities and add those up. That's what this is doing here. The number of heads of the possible x values, 0, 1, 2, 3, and 4. And these numbers, 1/16, 4/16, etc., those are the probabilities. It gives you the same answer. The point of this is supposed to motivate that formula, to say that formula makes some intuitive sense. That's why I'm talking about this. By the way, stop me if you've got questions. Okay? I do want to answer questions. Okay? Feel free to stop me. I know I'm going fast, as always. You gotta be thinking. Don't go to sleep. Pinch yourself. Yeah, that was an example that can be generalized to this formula here. That's an intuitive reason why this formula works. Why it's a good idea to define the mean of a random variable, a discrete random variable with finitely many possible outcomes in this way. Okay? And you will need to know that formula for the test and be able to use it. Make a chart. List the possible values of x and the corresponding probabilities. Make another column. Multiply each x times each p across each row. Add up that column that you made. I'll show you in the spreadsheet here in a minute. A few minutes probably. For continuous random variables, we're not going to talk about how to find it because you need calculus. If it's symmetric, then you could estimate the mean as being the center. It would be the center. That would be the center of mass, like a normal curve. However, with skewed distributions, you typically do need calculus to figure out where the mean is. So you're not going to have to find the mean for skewed distributions, but it is still basically the center of mass. If you've got a continuous random variable, and you know its density curve, that's its distribution, find areas under that to find probabilities. It turns out the mean is still the center of mass. And the median is still the equal areas point. Half the area to the left of the median and half the area to the right. But you need calculus to find those things, so we're not going to get into that. Mean of the sum of two random variables. Pretend you and a friend go bowling. Okay? You're about to bowl a game. Let x be your score and let y be your friend's score. Those are random variables. You don't know what you're going to get before you actually bowl. They're discrete random variables because you can only have whole number values for your score. Though there's so many scores you could get, it probably could be modeled by a continuous curve like a normal curve. Might be a good model, even though this is discrete. What would you guess the mean of the sum of your scores is over many, many games? Well, if you know your mean score and your friend's mean score, it should make good intuitive sense that you add your mean scores. What do I average when I bowl? I think I average maybe about 125. Okay, I haven't kept track of all my data. I've kept track of some of it. I think I average about 125 for my bowling score, so that would be my mean. If you bowl better than me and you average 170, that would be your mean. If we bowl together and group our scores, maybe because we're competing against some other group of 2 people, and add our scores together to get our total score, we could find the mean of the sum of our scores by adding up the individual means. 120 plus what I said, 125 plus 175. I forgot if those are the numbers I said. That would be 300. Hey, well, how about that? Not a perfect game, but combined score that sounds perfect. That should make good intuitive sense. This is the mean of our combined score. This is the mean of my score. This is the mean of your score. Add up means to find the combined mean. How do you interpret this? You imagine if you played many, many games, that this would be true. Okay? And in fact, for data, it would be literally true, but we're talking about models here. Models for our random variables, which again could be modeled by a normal distribution. So you got a normal distribution for me and a normal distribution for you. Mine's centered at 125, yours centered at 175. Essentially, you add those two to get the mean of the combined score distribution, which, if the individual ones are normal or approximately normal, the combined one would be normal as well, but would be centered on a higher value of 300. Again, we will apply these ideas in an example here soon. How about the difference of two random variables? I guess we're going to have to do the quiz pretty soon. I think after this we'll do the quiz. 2 sales associates, Greg and Marcia, keep track of their sales every day. X represents Greg's sales tomorrow, Y represents Marcia's sales tomorrow. Those are random variables. You don't know what they're going to sell tomorrow. Technically they're discrete because you could measure them down to the nearest cent. Though there's so many possible values, I bet using a normal curve would be best for these. What would you guess the mean of their difference in their sales is? And why might such a calculation be important? Well, it would be this formula right there, take the difference in their means. Why might that be important? Well, maybe you're the store manager and you want to compare how Greg and Marcia do. Okay? Who does better on average? Okay? Well, if Greg's average sales every day is $1,000 and Marcia's is $1,100, then that would be 1,000, that would be 1,100. 1,000 minus 1,100 is negative 100. The mean of x minus y would be negative 100. The fact that that's negative and the fact that x is Greg and y is Marcia